So welcome everyone on what is perhaps the worst weather day in the California Bay Area for the entire year. But I'm delighted to be here to speak to you all today and to give somewhat of an introduction to large language models in 2025, talking about how much understanding and intelligence that they show. I'm actually one of those both sides people that Lila was already mentioning. I have a PhD in linguistics, but somehow the Stanford School of Engineering has always been kind of nice at letting me pretend to be an engineer as well. Okay, for artificial intelligence, it's in a field with an extremely long history. And actually, we've got Ed Feigenbaum here today, who is certainly a representative from the very earliest days of that history. So there have been 60 plus years of artificial intelligence research. And actually, a year or so ago, we put together a great little video for which we got an Emmy Award on AI at Stanford, which you can find on YouTube. So if you want to find out about the history of AI, I encourage you to go and give that a watch. But I think it's fair to say that for so much of the world, AI seemed to appear out of nowhere with an enormous thud a couple of years ago. And that was when OpenAI's ChatGPT was released, and suddenly discussion of ChatGPT and artificial intelligence was appearing on all the major news shows and large magazine spreads and all of those sorts of things. And that then also caused these extremely rapid inflections in the corporate world. So it suddenly became mandated that every S&P 500 CEO had to talk about AI on their quarterly earnings call, and all the usual kinds of people started making predictions, with McKinsey saying that generative AI could add 2.6 to 4.4 trillion annually to the economy, and Goldman Sachs saying that AI would raise global GDP by 7% in the next 10 years. And, you know, there may be exuberance, but there was a reality to that people were just shocked by an amazing new capability that was just way beyond, certainly in terms of its sense of language understanding and generation and understanding of the world, anything that they'd ever seen before. So to give a sense of this, here's my cute little example for this morning. I've asked ChatGPT to say, write a sonnet praising Wikipedia in which each line begins with the letter W. And this is what it came up with. With wisdom vast that spans the world so wide, wielding the wealth of knowledge free to share, words weave through time where curious minds confide, whispering truths with patience just and fair, ... Wisdom and will sustain this noble dream. Wikipedia, our light, our endless stream. Now, this is maybe not the finest piece of poetry ever written, but, you know, it's kind of amazing, right? You know, you can give it sort of weird instructions like start each line with the letter W. It understands them perfectly and it delivers. And, you know, for those of you whose high school education was a bit rusty by now, right? Sonnets, they're 14 lines and have an A-B rhyming pattern, and that they're an iambic pentameter with wisdom vast that spans the world so wide. You know, it's totally done it. And this appeared on my screen in 3 seconds when I asked it to. You couldn't get a human poet to produce, well, they'd probably have difficulty coming up with a sonnet in which every line starts with a W period, but you certainly wouldn't get it in 3 seconds. So there is something quite amazing here. And, you know, it does just sort of have a lot of details there about the world. So that was amazing. So let me just sort of to have a bit of historical stuff about how we got to here. So the starting point was this sort of breakthrough in large language models. And large language models initially build on an extremely simple idea. It gets dressed up as unsupervised or self-supervised learning over enormous amounts of existing pieces of text. And all you do is ask your large neural network to play a game where you say, okay, the text so far is Ford plans to, and can you guess what the next word is going to be? Where, of course, since we have the whole article, we know what the next word is going to be. So maybe it's open, announce, close, something like that would seem appropriate. So in other words, we're asking our large language model to play Mad Libs like kids often do. So this is the audience participation section, so we can know that we're intelligent human beings. What happens when a unicorn poops? Unicorns aren't like other animals. They're magical, perhaps. They look like horses with hooves for feet and are something mane of hair. Colored mane of hair, flowing mane of hair. Okay, so we're all intelligent and we can play this game. And the amazing thing is that if you take a very large neural network with a ton of storage space inside it, and you feed into it a very, very large amount of text, and you do nothing else, out comes this large language model, which has an amazing ability to generate fluent text and seems to understand a lot about the world. And, you know, this was a complete change in direction, right? This wasn't how artificial intelligence was meant to be achieved, right? This seems so dumb on the face of it, right? We're just predicting the next word in turn from each context. And so it takes a little bit of thinking to think, well, how could you get anything that seems like, you know, knowledge of language, knowledge of the world, intelligence, out of this? But if you sort of think about it a bit more, you can kind of sort of get the idea, right? If I sort of do the knowledge case, right, you're going to have these contexts like the French president, and if you know the name of the French president and you can put Macron after it, you're going to be better at predicting, so it's good for it to learn that knowledge. And then if you start training your model on a few more 100 million words of text, some of it is going to be in different decades. And so maybe if you will start to learn that if earlier in the sentence it said in 1980 or something like that, you shouldn't say Macron, you should say, was that Mitterrand? Mitterrand. Okay, so you start to learn about history and you can predict people's political views and everything. And so this is what these models start to do. And so in the sort of this is all very recent, but in the late 2010s, they started off this model where we could build bigger and bigger large language models by throwing more compute, more data, and more dollars at them. And as you did that, performance in terms of text generation and understanding of the world just seemed to go up and up. And so that was the playbook of the first era of large language models. Just throw more stuff into ever bigger computer clusters and amazing progress would be made. Indeed, it seemed like we got a qualitative shift in what emerges, that we no longer seem to have a simple statistical predict the next word language model, which had actually existed since about 1980 and were used for things like spelling correction and machine translation. But rather we seem to have a machine that understands language and the world. Just to give you a sense of scale, if you're not up on all the latest numbers, I mean, here's a recent large open source language model, Meta's Llama 3.1. So it was trained on 15.6 trillion tokens, roughly words. That's a lot of books. It has an architecture where there are 405 billion parameters. So this unit of parameters are sort of individual floating point numbers in the neural network that are used to encode knowledge of language in the world. And it's trained for about 2 months on 16,000 NVIDIA H100 GPUs, the state-of-the-art GPUs at the time it was done. And it's these sort of NVIDIA GPUs with their massive floating point compute that have been so essential to these recent developments in artificial intelligence. So that was great, but it didn't actually do everything that we wanted. Because, you know, it gave fantastic language generation, but it didn't become a household name like ChatGPT in late 2022. And the reason for that is it generates some text after a piece of text, but not the piece of text you wanted. So if you ask GPT-3 who the US president is, by giving it the words, who is the US president, it generates some appropriate text after that, but it might say, who is the vice president? What are the levels of government? What is the difference between blah, 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 blah? It's not really answering your questions. And so the second era was then getting large language models to do what you actually want. And that's profoundly more useful. And that was done by a second stage of training to produce so-called post-trained or instruction-tuned models using an extra training process called reinforcement learning from human feedback, which again, I'm not going to get into the details of, but roughly you're showing it pairs of possible responses to a question or command and saying, you should choose this one, which gives the answer, not repeating on meaninglessly. And once that was done, we had the ChatGPT moment, and we had these amazing tools that you can use for all sorts of things. I'll just give one example that sort of starts to point into how you can start to so easily do research with these models. So suppose I want to know a little bit about climate change and pollution in my home country, Australia. One of the biggest polluters is AGL, a major energy producer. So I thought I'd look up about that, but they have a 168-page annual report PDF, and that didn't seem very fun to read. So I could give it to Anthropic's Claude and say, please read the 2022 AGL annual report, the most recent one that's out there. What does the AGL report say about the company's alignment with IPCC on climate action? And in a matter of seconds, it tells me. It says that the company is committed to aligning our business with the goals of the Paris Agreement and the IPCC's 1.5 degrees Celsius pathway. AGL has set a target of net zero emissions by 2050, and it's working on stuff. It gives some particular quotes about it. Now, this might seem a little bit too easy, because this is just sort of picking out and summarizing bits of the report that's there, but I could ask it a slightly more challenging question. I can then say, are there any comments that raise concerns as to whether AGL is fully committed to a net zero carbon emissions future? And they say, yes, there are a few comments that raise concerns. The company's decision to delay the closure of its Loy Yang A coal-fired power station by 2 years. This decision was made about concerns about the Australian electricity grid, but it's a setback for Australia's climate goals. And the company plans to invest in new gas-fired power stations. That's cleaner burning than coal, but it's still a fossil fuel. And well, it says it's going to achieve net zero emissions by 2050, but it hasn't given any transparency of how it's going to achieve that, right? So it seems to be able to do quite contextual, relevant understanding of what things might mean. And so that's a sort of a baby example with just one document of this now widely adopted across industry and in sort of public goods system of what's called retrieval augmented generation, a model where we give LLMs access to not just one document, but tons of documents. We have some information need that we're interested in. We do a usually neural network search to find relevant documents. The model then reads these documents, finds relevant pieces, and then can answer our questions about them. I want to give some balance in this talk. I mean, on the one hand, this is fantastic. On the other hand, it's so important that you're not naive about this and expect everything to be perfect. I've actually been doing a bunch of work with Dan Ho's group in the law school, and we've looked quite a bit at how good these RAG large language model systems are at actually giving legal advice. And you know, you don't want to trust them. So in a recent paper, for which I actually contributed very little, since it was mainly careful legal analysis of the results that were returned by these systems. You know, I really like these examples because it's just stunning what bad understanding of legal documents these models are actually saying. The commercial legal RAG system says when the lender receives the collateral that secured the fraudulent loan, this is considered a return of any part of the loan money. This was established in the Supreme Court case Robers versus US. But actually, Robers held precisely the opposite. The phrase any part of the property returned refers to the property the bank's lost and not to the collateral. And then this one says DM versus State has been overruled by Davis versus State. Also, the case Millbrook versus US was reversed by the same case at a later date. But actually, Millbrook versus US was a Supreme Court decision, and so the Nebraska Supreme Court couldn't overrule it and didn't even cite it in the judgment that's being talked about. So buyer beware if you're just going to be putting stuff into your term paper or legal brief straight out of a RAG system. But then, you know, we've gone on a lot from there. So we're now starting to see this new era of agentic AI where we're now hooking up these large language models to systems that can actually do stuff for us. And so that's then leading into sort of new opportunities and dangers of large language models doing things in the world around us. And so that's also a sort of a hopeful area in which one could hope to use systems that kind of go out and perform tasks as well as just simply get information for us. There are many other kinds of AI as well. I've just talked about large language models, but generative AI has also turned up for every other media. So there's images and sounds and video and things like that. I'm not really going to talk about those, but I did just want to show this one slide on image generation research. And the point I want to make here is really about the role of university research. So these days, I presume most of you have seen some of the wonderful images that you can get from generative AI, whether it's from tools from OpenAI or Midjourney or something like that. The interesting history was that the idea of diffusion models that underlies all of these current systems was actually invented at Stanford by an applied physicist, hence the use of the word diffusion, Surya Ganguly, in 2015. And so this was a picture from their first system. As you can see, it looks terrible. I think this is meant to be a bird, but you know, you can't really even recognize it's a picture of it. But you know, this was the first idea of using this sort of diffusion AI. And Surya, with another student, then worked on it some more a few years later. And so there was a 2019 system also actually with Stefano Ermon, computer science professor. And well, now we can at least see what's a picture of. So progress was made. And then there was further work on it at other universities, at Berkeley and the University of Munich, before it eventually made it out into the private sector and commercial products. But the first commercial products were also terrible. This is Midjourney version 1. I wouldn't want that to be a picture of my face. Midjourney version 2 wasn't much better. But you know, then things sort of rapidly progressed. Some of them looked fairly airbrushed for a while, but to the sort of modern world where we get these wonderful lifelike videos. So university research underpins, we spend a lot of time saying, what did OpenAI do? And, what's just come out of Google and Anthropic or Midjourney and so on. But university research really underpins these new developments and often precedes it by a decade. Okay. So now we're into era 3. So in the last year, the new thing is to say, well, we're going beyond having our instruction-tuned models and large language models to actually move into models that can think. And the new buzzword is test time scaling, which means you have your large language model think by spewing out a lot of words before it answers the question. I mean, again, this was a sort of a very simple idea that proved to have amazing legs to it. So even going right back to the early days, 2022, if you gave to the model a little math problem like this, the cost to produce a book is $1,000 plus $8 per book. The book sells for $20 each. How many books must be sold to make a profit? And said, generate some tokens for the answer. Well, it generated something in the form of the right answer. 1,250 books must be sold to make a profit. But if your math is good, you'll know that that's not the answer at all. It just came up with a random number. But then people discovered this wonderful little trick that instead of just putting down the text there I had in purple, if you stuck at the end of the text, let's work step by step, or some phrase like that, that gave it this sort of, the large language model, a kind of mind hack nudge, and it said, okay, I meant to actually work it out systematically and give the answer, and it tried to. The cost of producing one book is $1,000 plus 8 equals $1,008. The cost of producing 2 books is $1,008 plus 8 equals $1,016. This is starting to look good, but if you read on a little, it starts to go bad, because cost of n books is 1,008 plus 8n. Whoops, it's a little bit off there. And if you get further in, there's some really, what do they call it now? Alternative math? There's some really alternative math being used in the middle here, where the steps don't actually follow each other. But somewhat amazingly, it's then through a couple of steps of alternative math actually comes up with the right answer and gives it at the bottom. But that was in 2022. In 2024, this has all been cleaned up. And if you ask OpenAI, GPT, for this question now, well, not only is the formatting much, much better, look at that beautiful markdown with math, but the working out is completely correct. Total cost equals 1,000 plus 8x. It does the algebra correctly. It gives you the right answer, and it realizes that you can't have a non-integral number of books, so you have to sell 84. Awesome. So that was already pretty good. But then in the last few months, there's been even more development of that to say, well, maybe if we just let large language models think for a really, really, really long time by rabbiting on and producing a lot of tokens, we could get them to do all kinds of really difficult stuff, like Math Olympiad questions and difficult coding problems and things like that. And we can train the models to sort of practice thinking in this way and getting the right answer to the problems. And the amazing thing is this seems to work. So this was really sort of first shown by OpenAI in their O1 model. But I'm going to show here the model of our Chinese compatriots with DeepSeek's recently released R1 model. So I can ask it, find 2 3-digit palindromic numbers that sum to a 4-digit palindromic number. And so DeepSeek explicitly says it goes into think mode with that think and angle brackets. This is teeny because there's so much of it, and it just sort of starts rabbiting on. Okay, so I need to find two 3-digit palindromic numbers that when added together is on a 4-digit palindromic number, and none of the numbers can start with a 0. Let me break this down. First, what's a palindromic number? It's a number that reads the same forwards and backwards. For example, 121 or 1331. So a 3-digit palindrome would have the form ABA, where A and B are digits, and A can't be 0. Similarly, a 4-digit palindrome would have the form ABBA. Let me check 1221 is a palindrome. Yeah, so ABBA is correct with A not equal to 0. So I need two 3-digit numbers, both palindromes that add up to 4-digit palindrome. Let's denote 3-digit numbers as ABA and CDC, since they can be different. But wait, maybe they could be the same palindrome. But adding the same palindrome would just be doubling it. Let's see. The smallest 3-digit palindrome is 101. 101 plus 101 equals 202, which is a 3-digit palindrome, so too small. The largest 3-digit palindrome is 999. 999 plus 999 equals 1998, which is a 4-digit number, but 1998 is not a palindrome. So adding the... this is about 2% of it. It goes on for thousands of more words saying all of that, and it's thought through it all, and it's come up with some formulas to determine things, and then it's getting close, and it says, hence my main thought streamline. Possible sums are only 1111 and 1221, determined by the formula. There was some work it did above. Two types of palindrome pairs, numbers with middle digit 0 and leading plus trailing A plus C equals 11, e.g. 202 plus 909 equals 1111, correct, beautiful. Numbers with both leading and trailing digits summing 11 equals A plus C, and middle digits summing 11 B plus D. And this bit's interesting. It says, for example, 212 plus 909 equals 1121, which isn't a palindrome. Or wait. Another example is 232 plus 989 equals 1221. 8 plus D equals 3 plus 8 equals 11, right? Whereas the earlier example where it was 1 plus 0, that equals sort of 1, not 11. So it goofed up there, right? So it sort of does these little goofs and corrects itself along line. Therefore, focusing on styling both sums approach. Therefore, to conclude, the examples answering the problem will be, and it gives 2 examples of answers that work. Amazing stuff. This is just an amazing level of reasoning. And so the question now is, is it just the case that we can now sort of scale this kind of test time thinking, and we will have models that will be able to do whatever we want, that they will discover new science, they can work on arbitrary math problems and things like that? Honestly, I kind of don't believe it'll work. I mean, this may show that I'm turning into a grey-haired older person, but I'm just sort of somehow suspicious that for all of these abilities, it still seems like we've sort of got something more like a simulacrum that sort of lays down text based on all the text it's written of the kind of patterns it's going to use, and it doesn't necessarily really understand things deeply. And you see some signs of that even when it goofs a little, right? That it said correctly the condition that the middle digits had to add to 11, but then suddenly it puts down 2 numbers that don't add to 11, and then it corrects itself and goes back. I mean, it's very complex. But I mean, I really do feel that somewhere along the line, we still need a model with more of a world model than these current large language models have, because, no matter how clever they are, there still are these models that are sort of producing long strings of text tokens rather than having sort of any kind of joint model of the world. But, that's really hard to know. I mean, it's just amazing the progress that's been made with these models. It sort of feels like at this point it's a mistake to bet against them, right? There have been people who've been saying for a decade, oh, you'll never be able to do X, you'll never be able to do Y with these models, and yet we keep on finding ways to do more and more with these models. Let me just also say a little bit about the non-technical lessons from DeepSeek R1. I think one of the non-technical lessons is that US so-called frontier AI companies do not actually have a huge technical moat. It seems like they're at most 6 months ahead of other groups such as companies in China. And so this makes it clear that the control and development of AI cannot be determined by just US policies. But if we go beyond that, I mean, I think there's a weird state of affairs in the world at the moment that our leading US AI companies are incredibly secretive and have decided that they're not going to be revealing any of the details about how their models work and are built. Actually, I should leave one out, with the exception of Meta. Meta is still building open source models and distributing details of how they built. So while there are many other very good reasons to hate on Meta, in terms of open source engineering of large language models, Meta is my friend. But that's not true of Anthropic, OpenAI, or even Google these days. So there's this weird fact that currently the best way to learn the details of modern LLM engineering is to read the tech reports of Chinese companies, which are open and detailed. That seems a sad state of affairs given the last 70 years of the US leading as a country advancing open science. And so I really believe that this isn't a tenable state of affairs long term, that if the US is going to maintain a leadership role in AI, it's really necessary that more is done to support universities, to train engineers, and to support the kind of open software and knowledge that allows people to learn things and start new startups that then become part of productive US industry. Okay. How many minutes should I? Okay, a couple more minutes. I will finish up. Okay. Yeah. So I had a few more slides on intelligence in general, which I think maybe I'm going to just have to skip. So let me just say this bit at the end. You know, you can absolutely go wrong using AI. You can assume that everything an LLM says is correct. We saw how that's not true. You can also think they're magical. I mean, you can say, dear large language model, pretend you are Warren Buffett and tell me what stocks I should invest in. And it will. But that doesn't actually mean you're getting good investment advice. But, you know, conversely, you can go to the other extreme and assume that they're good for nothing. And that's a huge mistake. I mean, these large language models are just amazing in their abilities. They're better at absolutely everything that has been explored in natural language processing and knowledge representation and reasoning over the past 60 years. So they can be used to increase your productivity, to learn new knowledge in all sorts of ways. And they give huge order of magnitude gains versus many other technologies that have been worked on. So I encourage, for any of you that are more on the humanities side of things and haven't been keeping up with everything, you know, I really encourage everyone to play with generative AI. Part of the beauty here is this is so easy to play with, you know, until large language models, if you wanted to get into any of this stuff, we had to say, well, first of all, you need to learn some Python, and then you probably need to take an intro machine learning class, and then you could do blah, blah, and maybe build a classifier where, you know, these days, if you can use a web browser, you get a text box and you write some text and you can see what a large language model can do. There are just great opportunities of thinking of these models as a kind of intern or assistant that you can work together with. They're great at being told what to do, kind of like a human assistant, and you should expect them to make mistakes as human assistants sometimes do. But you can also be amazed at what they can achieve. And I really think it's important to remember that as amazing as these models are, they are going to get better. So next year's models and the year's models after that are going to be even better at assisting in all of these things. So we should really be thinking now about the future with the understanding that the technology we're going to see for the rest of these 2 days is the worst technology that we're ever going to deal with in the future. It's going to keep on getting better from here. Thank you.
You mentioned some of the limitations of RAG and other things, where companies have a lot of data they want to be used in answering questions from the LLM. What are your thoughts on the various approaches? Could they use fine-tuning, but in other cases where the information is being refreshed all the time, for example, news or new code being generated by a company? What do you think are the best solutions for that?
Right, so RAG is a good technique, right? Compared to just asking a plain LLM answers, RAG is much better because you can not only put in your own company's or industry's information, but simply that you have the documents there reduces the rate of hallucination. So a RAG system typically would have half the rate of hallucinations making stuff up as just asking a language model by itself. So that's useful, but half as many things made up is not the same as nothing made up. And so there are a bunch of other techniques that people can use and explore for reducing the rate of hallucinations. You can ask for multiple answers and check for consistency. You can do post-training of models to lower their rate of hallucination. We've worked on that with our direct preference optimization algorithm. And all of these things are techniques that can lower the rate of hallucinations and get them lower, but still not that close to zero. Yeah.
Oh, can I go?
Yeah.
Chris, before we have a mixed audience of people who know a lot about computer science and people who don't. So for that audience, I want to just start off by congratulating you again on your election to the National Academy of Engineering.
Thank
you. People who are not in engineering don't know what a big deal that is. That's like a life achievement. So fantastic.
Thank you.
The question I want to ask is, it really relates back to some words that you used, but you just passed over them quickly. Knowledge representation. You talked about these models that keep adding capability year after year after year. Have any of them incorporated the what you might call the legacy of the past, namely knowledge graphs and things like WordNet, where relations are explicitly made between the words and the concepts?
I mean, I think the answer is sort of both yes and no, that there's not an explicit knowledge graph of the kind that people imagined a decade ago. But, instead you have these billions of floating point numbers. But I think the right way to think about things, and indeed you see strong evidence of this if you poke hard enough at neural nets, is those billions of floating point numbers end up as just like a large amount of memory, right? So if you've got, your laptop computer or any other computer, it's not that it explicitly has, graph structures inside it. What it has is, a lot of memory addresses, and you can be a clever computer scientist and say, I'm going to store a graph in these memory addresses. I've come up with a scheme of here are my pointers and my units and things. Well, a large language model has billions of floating point numbers, and it can decide to structure those however it wants, and there are explicit mechanisms like attention, which is a kind of pointing mechanism, so that it can build graph structures inside its floating point number space. And we absolutely see it doing that. One of the clearest examples from my domain of language is you can ask these models and or look at their representations and look for syntactic parse trees of the structure of sentences, and it's constructing parse trees for sentences. So although we're not training it explicitly to parse sentences, it's building up its own knowledge structures based on having seen these huge amounts of text. Okay, maybe I should call it. Thank you.